we said that computers, well, there are true random numbers and there are pseudo-random numbers. A true random number is generated from some natural source, but that's generally hard to collect that information to generate random numbers for computers. So we have algorithms that generate pseudo-random numbers, not true random numbers. The idea of the algorithm is to produce a sequence of numbers which exhibit randomness. And there are different measures that we spoke about last week of what do we mean by randomness. Some simple things that you can think about are that the numbers, if we look at binary values, that the bits should be equally distributed, or that there should be equal number of zeros and ones in a sequence. So we have a large sequence of zeros and ones. They should have equal number of zeros and ones. There should be no dependence upon one number compared to the previous number. They should be independent. And not just in the entire sequence, but if you look at subsequences. That is, I take a section of a sequence, and again, there should be an equal number of zeros and ones. So there are different measures of on a sequence of numbers whether they exhibit randomness. We went through, or we started to go through this number generator, random number generator. Let's continue with our examples. We quickly went through a few examples. We won't go through the calculations again today, but one of them was if we use this generator, xn plus 1 equals our multiplier a times xn, the previous value in the sequence, plus some increment c mod m. If we take the values of the multiplier to be 7, ignore the increment, c equals 0, so that we don't add something on, and mod 32. If we choose our initial value, our seed, x0 as 1, then we get the sequence 7, 17, 23, 1. And once we get back to one of the values already in the sequence, then we'll keep generating that same set. So 7, 17, 23, 1, 7, 17, 23, 1, and we'll go forever if we keep incrementing the value of n here. So we effectively have 4 different numbers in our sequence. With this pseudo-random number generator, or with any sequence that we want to generate, we'd like to get a long sequence, a sequence with a long period, so that we generate numbers that are different. With a short sequence, we only have these 4 values available to us. After that, there's repetitions, and repetitions is not random. So we only look at those original occurrences of 7, 17, 23, and 1. So in this case, our sequence is of length 4. There are 4 numbers in the sequence. And the second example, or another example that we by changing the value of the multiplier A from 7 to 5, then we get this second sequence, which is 5, 25, 29, 17, 21, 9, 13, and then back to the seed 1. That is, x0 is 1. Here we get back to that seed value. So the length of this sequence is 9 values. That is, there are 9 unique values, and then we repeat them, and we'll continue repeating them. So we will consider that better than the previous case, because we got a longer sequence of original numbers. How do we get the longest possible sequence? Or first, what is the longest, in theory, what's the longest possible sequence in these two cases? 32. With a mod 32, the values as the output can be between 0 and 31. That's all. So the maximum length we can get is 32. In the first example we got 4. In the second one we got 9, so that was a bit better. Ideally, if everything was perfect, we'd get 32 different values. Now there are ways to get 32 values, and we saw the first example, if we have A and C equal to 1 and M equal to 32, we will get 32 values, but it would just be incrementing 1, 2, 3, 4, so it would not be random. So it's not just about the length, the sequence itself still needs to exhibit randomness. The sequence 1, 2, 3, 4, or 0 up to 31 is of length 32, but it's not random. So we want a random sequence as long as possible. The sequence length depends upon M. Therefore, to get a larger potential random sequence, increase M. And we get to what a good value of M should be. For example, in a 32-bit computer system, set M to be the largest integer that you have available, or close to. It turns out that, okay, set M to a large value. Turns out people have done analysis, it should be prime. So this is an example of a prime number that is very large. 2 to the power of 31 minus 1 is a prime number. And the other values, if you set the increment C to 0, there are only several good values of A, the multiplier. One example is 7 to the power of 5, 16,807. So if you use these two values and C equal to 0, it gives us a reasonably good random number generator in that the sequence is long and those numbers in that sequence exhibit randomness. So just an example of an algorithm that generates pseudo-random numbers. Of course, the correct parameters, or the optimal parameters, need to be selected to give a good random sequence. But of course, if you know the parameters, you can predict the next value in the sequence. So if an attacker needs to work out what random number you're going to use, then all they need to know is that you're using this generator and know the parameters that you're using, and they'll be able to work out, okay, if the previous random number was 25, they can easily determine that the next random number will be 29. In some applications, we need random numbers that an attacker cannot guess. They cannot predict what the value will be. So that I choose a random number and send that to someone else, I don't want the attacker to be able to guess what random number I chose beforehand. But if they see something about the sequence, okay, yesterday I chose the random number 25 and sent it to someone, and they find that out, then the attacker may be able to predict that the next number I'm going to choose is 29. They would be able to do that if they knew I was using this generator, the value A equal to 5, M 32, and so on. So that's the problem with such an algorithm. If the attacker knows the parameters you're using, they can easily predict what the next value will be. What about another example? and I don't think it will go through on the board, the slides have it, Blum-Blum-Shub generator, a different algorithm, and considered cryptographically secure. That is, it's a good pseudo-random bit generator. It generates bits in a random sequence of bits. Just briefly to show how it works, we have two large prime numbers, P and Q, such that P mod 4 equals 3 and Q mod 4 equals 3. That is, we get the same value when we mod them by 4. We calculate n equals the multiplication of those two prime numbers, P and Q. So we have two large prime numbers. Large means usually tens of bits in length, possibly hundreds of bits, as large as we can get in prime numbers. Multiply them together and we get a very large number, n. We choose some number s, a random number which is relatively prime to n. We'll cover in the next topic a little bit more about the modulus and relatively prime, but relatively prime means that the two numbers have a greatest common divisor of 1. The greatest common divisor of s and n is 1. They can't be divided by anything else except for 1. So we choose some value s that meets that criteria, and then we generate a sequence of bits, bi. The first initial step, we calculate x0 as s squared mod n. So take our value of s, square it, mod n, our large number, and then go in a loop. This is not formatted very well. These two lines at the bottom should be within the for loop. So loop for I forever, I equals 1 for as many bits we want to generate. X is the previous value, so x0. x1 will be x0 squared mod n. And then from the last bit, or from the last value, the last digit in the integer there, grab the bit. That is mod by 2. An example is shown here. Some values of P and Q, 383 and 503, two prime numbers. When we mod by 4, we'll get 3. Some random number s, which is relatively prime to n. Some initial value, 20,749. We square that value and mod by n, and we get the answer 143,135. And because it's odd, it's an odd number, the last bit, when we mod by 2, we get 1. So the bit, which is output, is 1. We take this number, square it, mod by n, and we get this 177671, and mod by 2 and we'll get 1. That is, if it's an odd number here, the bit is 1. If it's an even number, the bit is 0. And we keep doing that, and this is our random sequence, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, and we keep going. That's the random sequence that we're generating there. And that is considered a good pseudo-random number generator in that it generates a sequence of bits which have the properties of, we'll get equal number of 1s and 0s in the subsequences and in the entire sequence. The repetition of the sequence, the sequence itself is very long because we're using these large values here. So it's considered what's called a cryptographically secure pseudo-random bit generator. There are others. So this is just two examples that we can use different algorithms to generate random numbers. So they are algorithms that were designed specifically for generating random numbers. That's their purpose. In addition, we've got another approach. We can use our block ciphers, which were designed for encrypting data to generate random numbers. Because a block cipher takes as input some structured plaintext, and the idea is to produce some ciphertext which appears random. So a block cipher generates random values as well. Because from our encryption perspective, if we have a structured plaintext, the ciphertext should have no structure. That's ideal with our encryption. No structure means it appears random. It's random output. So our block ciphers can be used to generate random numbers or pseudo-random numbers. And there are different ways that you can use the block cipher to generate a pseudo-random number. Here's the example. We can use our different modes of operations, the counter mode or output feedback mode. Our counter mode, remember, we just take some initial value, encrypt a block, and increment that value to encrypt the next block. So in this case, what we do is we take some initial value, V, some key K, and encrypt V, and we get some ciphertext out. And because if we're using a good cipher, block cipher here, then that ciphertext out should exhibit randomness. It should have no structure in it. It should have an equal number of zeros and ones. The sequences within them should not be predictable. So we get a random sequence or a pseudo-random sequence of bits output. And then we just modify the input, increment that, same key, encrypt again, and we'll get another sequence of bits out. So that's a way to generate a pseudo-random sequence of bits. What's the difference between using a block cipher and one of the previous algorithms? Anyone have an idea? Say using DES in here as the encrypt operation compared to using blum blum shub or the previous pseudo-random number generator. What's the difference? Which one's better? I don't think it says in the lecture notes. Which one's better? Or what are the advantages and disadvantages of using, say, DES here versus using one of the algorithms in the previous slides? All right, another way to think of it. I give you an assignment homework task. I ask you to implement DES, or I ask you to implement one of these algorithms. Which one's going to be easier to implement for you? The 4-line algorithm here, or the 5 pages of DES? Well, this is going to be easier to implement. That is, these are built for generating pseudo-random numbers, and therefore they can be generally implemented so that they run faster. That is, they're easier to implement and perform better. And same with the previous algorithm. Whereas DES and other ciphers are complex algorithms in many cases. So the implementation of them will perform worse. So we can use our block ciphers here, but in terms of performance, they may be slightly worse than the dedicated pseudo-random number generators. In terms of security, that is, do they generate a sequence that exhibits randomness, then they're about equivalent. There are different measures, but using DES or one of the other ciphers here produces good security. It produces good pseudo-random sequences. Another quick example is a standard for pseudo-random number generators, the ANSI standard X917. Again, cryptographically secure. It produces good random sequences. It relies on triple DES. In fact, it uses triple DES 3 times. It takes as an input some date-time value as a 64-bit value, some seed value V, and a pair of 56-bit keys. Produces a pseudo-random number as output and a seed value which is used again in the next step. EDE refers to triple DES. Remember, triple des, 3 operations of des. One way to do that is to encrypt, decrypt, encrypt. So in fact, here we use triple des 3 times. Take the date, time representation, use our keys, our input seed value, or input value v. See how we apply that, some XOR operations. We get a random number out, which we'll use, and we get a new value of v out. And then if we want to produce more random numbers, another 64-bit random value, we'll use this and do the same operation. So we can use block ciphers in different ways to produce pseudo-random numbers. So there are good algorithms for producing good, strong, random sequences. The main selection criteria will be then the implementation. Is it easy to implement? Is it fast to execute on the software or the hardware platform that you're using? Now, so that finishes our discussion of pseudo-random number generators. But related to that, we've spoke about block ciphers. We have also stream ciphers. And a stream cipher, we encrypt usually 1 byte at a time using an XOR with a pseudo-random byte. So this is the connection. We take our plaintext input, a stream of plaintext, that is a continuous sequence of bytes that come in. We use a key. We have some block that generates our key stream, which is a pseudo-random sequence of bits or bytes. So we can use a pseudo-random number generator here, as long as it takes a key as an input. It produces some sequence. It's given here as lowercase k, which is 1 byte, a random byte. We XOR that with our 1 byte of plaintext, and we get 1 byte of ciphertext out. And we can keep doing that. Keep generating more bits in our random sequence, more bytes. Every input byte of plaintext, we XOR with a byte from our random sequence. So that's the general operation of a stream cipher. They differ by how this block is implemented, the pseudo-random byte generator. And decryption is easy. We take the same key, the same generator, and we simply XOR the ciphertext with the same value here, and we'll get the plaintext, because the XOR operation is an inverse of itself. Plaintext XOR k gives us C ciphertext. C XOR the same value of k will give us the plaintext. So very easy to implement. We just generate random numbers and XOR. The output of this white rectangle, the generator here, is called the key stream. It's a stream of bits which we use to XOR with our plaintext or ciphertext. Okay, so our key is a fixed length. Let's say it's a 64-bit key. Then this generator here must take this fixed length key, and when we apply it again, it must produce a different value of k output. So one way we can do that, if we go back, this would be one way to do it. Our key is in fact k1 and k2 combined. We have some seed value, vi. We apply these operations, which is really using triple des 3 times. We'll get one random value, a 64-bit value out here, and we'll get a new vi out as well. So if we need to generate another 64 bits of random output, we'll just do this again. Same key value, but the difference will be this input here. That is, the next time we do it, this will be input here. So we'll get a different random R coming out here. So yes, we use the same fixed length key, and this must generate a sequence of bits, which exhibits randomness. And it's a stream generator in that if we keep applying this, we will keep generating random bits for as many as we need, depending upon the length of our plaintext. If I go back to the example of a voice conversation and I want to encrypt that, I'm using voice over the internet and I want to encrypt it. When I talk, the voice codec generates bits, let's say a byte of my voice, and the encryptor will just take a random input, K, the key stream, take, say, a byte from the key stream, XOR, and send my encrypted voice across the network. And as I keep talking and generating more bytes, then the pseudo-random byte generator keeps generating bytes, different bytes. So same as what we've already said with our pseudo-random number generator, we need to generate a key stream that has a large period. It shouldn't repeat. We want it to be as long as possible. If it repeats, then we get some structure in the output ciphertext. And the key stream should be a pseudo-random number. That is, approximate a true random number sequence. And of course the key, because it would need to be secret, needs to withstand brute force attacks. The key itself needs to be long enough. So note the difference between the key stream and the key. Uppercase K here is the key. That's some secret that's input to the pseudo-random byte generator. The key stream is this lowercase k here. That is the output. And that's what we use to XOR with the plaintext and ciphertext. And compared to block ciphers, stream ciphers are often simpler to implement and faster. That's their advantage. So we use them when we need that fast, simple implementations. Block ciphers, we can reuse keys. We'll see with stream ciphers, we normally need to keep changing the key. We'll just go through one example of a stream cipher. So this is a cipher that was built specifically to be a stream cipher. We saw in the modes of operation that we can take a block cipher and turn it into a stream cipher by using a mode of operation that selects just a subset of the bits of the output of the block cipher. So we can use block ciphers to create stream ciphers, but there are also some ciphers which were designed specifically, and their sole purpose is to be a stream cipher. RC4 is one such cipher. It was designed by Ron Rivest, and we'll see him also design another important cipher, RSA, shortly. It's been used in different applications, common applications. Secure web browsing, it's been used in wireless LANs, in the WEP encryption in wireless LANs. They used RC4. It's very simple and efficient implementation. So in terms of performance, it's good. It can use variable size keys from 8 up to 2,000 bytes, or 2,048 bits. Sorry, not bytes, bits. There are some limitations of RC4 in terms of security, but there are no known attacks. So in theory, there are some limitations, but there are no known practical attacks if it's used properly. That is, if you use a large enough key and that you use the initial values in an appropriate way. It uses some initial values. That is, if you don't keep using the same initial value, it should be okay. But if you reuse the same IV, there are some practical security attacks that can defeat RC4. And in fact, RC4 was used in the wireless LAN encryption called WEP, Wired Equivalent Privacy. And it was shown to be very weak security for wireless LANs. It wasn't necessarily a problem with RC4, it was the way that the initial values and the keys were used by the wireless LAN for RC4. So the algorithm itself is considered secure, but you need to use it in the right way. WEP is used in your Wi-Fi, your 802.11 wireless LAN. No, it's not related to frequency hopping. It was just used as a stream cipher. So if you turn on WEP, then all the data you send is encrypted using RC4. That is, RC4 generates a random key stream and it XORs with the data that you're sending. Yeah. Frequency hopping is a different issue for security. It has a set of parameters and variables in the algorithm. We will look at the algorithm, the basic algorithm, and go through an example with a simplified version, just to demonstrate it. A variable length key, K, so 8 bits up to 2048 bits in length, so the user can choose the length of the key there. It operates on some state vector, S, which is 256 bytes. So think of it as a vector or an array of 256 one-byte values, or one-byte elements. And also has some other temporary vector of the same length, T. And it generates the key stream lowercase k is generated from S, the state vector. We need to initialize the value of S, the state vector, to value 0 up to 255. So S is a vector with 256 one-byte values. The first byte will be 0, the second byte 1, the last byte 255. That's what the first step is. And T is initialized to repeating values of the keys. So the user chooses a key, uppercase K here, some digits. If we think T is a 256 element vector, then if our key is 1, 2, 3, 4, then we just repeat that to fill out the vector. 1, 2, 3, 4, 1, 2, 3, 4, and so on to fill out the 256 values. That's the first step to initialize things. We use T to perform some initial permutation on the state vector S. So we rearrange the elements in S. We'll see the way that's rearranged in a moment. And then another permutation on S. And from that, generate that output key stream, 1 byte K, our random byte. And then we'll do that again to generate another random byte K, and again to another random byte K. For every K that we generate, lowercase k here, we can encrypt by taking that value of K and XOR with a plaintext P. We'll show that algorithm with an example. The next few slides show the algorithm, but let's go through an example to demonstrate it. To give an example, I'll use a simplified version of real RC4. So RC4 has a state vector S, which is 256 elements. Each element is 8 bits in length, 1 byte. So if I was to write that down, we would not have enough space. So what I'm going to do is reduce that to an 8-element vector instead of 256. And every element is not 1 byte, it's just 3 bits. So in RC4, every element in our state vector is an 8-bit value, so it can range from 0 up to 255. In our example, every element in our 8-element vector is a 3-bit value, so it can range from 0 up to 7 in decimal. So I can write S, our initialization of S, set it to, in the real RC4, values 0 up to 255. In our case, we only have 8 elements, so set it to values 0 up to 7. So that's S, our state vector to get started. 8-element vector. As an input, we have a plain text P, 4 elements. I've chosen the plain text, and I've chosen a key. So this is what the user would choose, the key, and have the plain text. 1236 is the key, 1222 is the plain text. We want to encrypt that plain text to get some ciphertext as output. The other vector we use, T, is the same length of S, and it's initialized by setting it to the value of the key and just repeat the key to fill up the vector. In our case, our key is 4 elements, T is 8 elements, we just need to repeat the key twice. So T becomes 1236, 1236. So that's step 1 in the algorithm. That's just done at the start. Step 2 is to use this value of T to rearrange S. And so this slide shows the first step. Just initialize S and initialize T to be the same as the key, but just repeat the key where necessary. And this is the initial permutation of S. What we do, and we do it 256 times in the real RC4. J is initialized to 0. Take the current value of J, add the value of Si. So for I equal to 0, Si is the first element, element 0. And then similar for the first element of T, element 0 from T, add them all together, mod 256. We'll get the new value of J, and then we swap the 2 elements in S, in the state vector S, swap element I and J. This should be inside the for loop, so this should be indented, that swap there. Let's do that on a simplified case. So remember, just in the simplified example, we're not using 256 elements in a vector, we're using just 8 elements. So it's not going to be 0 to 255 mod 256, it's going to be from 0 to 7 mod 8 to keep the thing small. So what we do for I equal to 0, calculate the new value of j, where j equals the old value of j, 0, plus si, s0 in our case, plus t0. S0, our state vector, is 0. T0 is 1. So our new value of j is 1. J equal to 0 plus t plus s0, which is 0, plus t0, which is 1, where t depends upon our key. And now the second step, and it should be inside the for loop, is to swap S0 with S1. That is, swap Si with Sj. I is currently 0, j we just calculated to be 1. And swap just means swap the elements. So S becomes seven. So the output of this first iteration is the new value of S, our state vector, where the first two elements have been swapped in their position. So we're permutating S, that is rearranging the elements. At the output of this, S is still going to be 8 elements, and it's still going to contain the values 0 to 7, but they're just going to be rearranged. We're doing step 2. That was the first iteration in step 2. We need to repeat that for I equal 1, 2, 3, 4, 5, 6, 7. We'll only do it for one more iteration, just to demonstrate. So that was for I equal to 0. Now we set I equal to 1. J equals the current value of j, which is 1. So we just repeated that step, but with I equal to 1. Let's go through it. I equals 1, so we're doing these two steps here. J equals the previous value of j, which is over here. We calculated j to be 1 previously, plus si plus s1 plus ti, which is plus t1 in our case, because I equals 1. S1 is 0. Our state vector, remember, index 0, 1, so S1 is 0. T1 is 2. So j plus si plus ti is 1 plus 0 plus 2 is 3, mod 8 gives us 3. The new value of j is 3. Then we swap si, s1, with sj, which is s3. That is, from here, swap element index 1, which has a value 0, with element with index 3, which has value 3. Swap 0 and 3. And the new S becomes 1, 3, 2, 0, 4, 5, 6, 7. If we keep going for the other values of I equal to 2 up to I equal to 7, you'll eventually get this value for S. That was step 2, which is just the initial permutation on S. Now we need to generate our random values as an output. We're going to use S and permutate it again to get some output lowercase k, the random key stream. And then we'll simply do an XOR. So we'll do one example of the next step 3 and then do one example of encryption. Step 3, the stream generation. We want to generate our random key stream, the bytes, the random bytes that come out. And simply once we get a random byte, lowercase k, we'll XOR it with our byte of plain text. In our case, we don't have bytes, we have 3-bit values. What we do, in a loop, we have I and j, new values of I and j. Increment I, mod by 256, j equals the previous value of j plus si. So grab the value from S according to the index, swap those two values of S, so permutate S based on I and j. So we'll have a rearrangement of S, get this temporary value t, where we take the two values of S, mod by 256, and that becomes our index into S, and the value of S of t will be k. K is our random value as an output. We'll generate a value of k just to show this step, and then talk about the output from all the steps. What have we got? So first step, I and j are initialised to 0. I equals I plus 1, that is I equals 1. We're mod by 8 in our example. So the new value of I will be 1. J equals j plus s of I. J equals the initial value of j, 0, plus s of I is 1, s1. What is the value of s1? Well, from our state vector here, s1 is 3. Because I has been updated. I and j are initially 0. We modify I in the first line. I becomes 1. So j becomes 0 plus s1. s1 is 3. S0, S1 is 3, so mod 8. J becomes 3. Swap SI and SJ. SI or S1 and S3, and we'll get the new value of S. Swap S1 and S3, that is swap 3 and 4. So instead of 2, 3, 7, 4, we get 2, 4, 7, 3. That was this swap operation. T equals SI, S1, which is 4, plus Sj. J is 3, S3 is 7. We've got this right? Sorry. Yep, S1 and 3. Sorry, Sj, J is 3, S3 is 3. That is S1 is 4, S3 is 3. That's this step for the value of T. Our random byte that is output from the first step is 5. Our pseudo-random byte. We would take that byte and XOR it with our first byte of plaintext, 1 and 5. XOR those two values, treat them as bits, 3-bit values, XOR them, and you'll get the output ciphertext, the first byte of the ciphertext. We would do these steps again. See, this is in a loop. We'll get a new value of K. XOR it with plaintext 2. And again, I get a new value of K, XOR with the third element of the plaintext, and so on. We just keep repeating this for as long as we need, depending upon the length of the plaintext. We're not going to go through any more steps. If we keep repeating this, then our first value of K was 5. This is lowercase k here. It's not the key from the input, it's the key stream that's output, the random output. 5, then the next iteration 6, 0, 1. So we just XOR 1 and 5, 2 and 6, 2 and 0, 2 and 1, and we get our ciphertext as output there. If we keep iterating here, we'll get our key stream, random key stream. How long will our key stream be? we can keep going. It depends upon what plain text we have. We just keep generating random numbers. So this is the random sequence which is output. And in fact, you can use RC4 as a simple random number generator. Simple but strong random number generator. Instead of encrypting, just do the steps and take lowercase k as the output, and that's your random numbers. We went through this example not for you to have to remember all those steps. The steps are quite easy. To demonstrate that compared to, for example, simplified DES and DES, this is still much easier than DES. The operations are quite simple. Initialize two vectors. Go through a loop 256 times and just rearrange two values in vector S. And then for each input plaintext byte, calculate these indexes, swap two values in the state vector, and generate the output keystring value k. So again, in terms of implementation compared to our block ciphers, this is extremely simple to implement, and therefore much faster than in using a block cipher for a pseudo-random number generator or for a stream cipher. So it's performs much better. So RC4 is just one example of a stream cipher algorithm, an algorithm built just to be a stream cipher. It can also be used as a random number generator, because what it does is generates random numbers and simply XOR those random values with the plaintext. The example I went through, you can download that. It may be in your handouts, or it may not be, and if it's not, it's on the website. So you can see the other steps for getting to these values if you want to. Any questions on random numbers, pseudo-random numbers, or stream ciphers? Because we're about to change topics, that is, to something completely different. Yep. Why is it called Blum Blum Shub? And I don't know, I assume that's the correct pronunciation because there was 3 people that developed it. Blum, Blum and Shub. I think they were husband and wife. I think so. Blum and Blum. Shub, I think, was not related. Yeah. So just the names of the 3 people. The next cipher we'll see, not today, but the next cipher we'll see is RSA, developed by Revest, Shamir and Edelman. So another cipher developed, named after the creators. One of them was the creator for RC4. No, the name of the creators. I think so, yeah. So the next form of encryption that we're going to look at is asymmetric key encryption. The block ciphers, everything we've looked at is symmetric key encryption. Both the sender and receiver must have the same key. It must be a secret as well. The next, or the alternative, is asymmetric key encryption, or public key encryption, where there are two keys, but they are different. They're somehow related, mathematically related. So the sender has one key, the receiver has the other key. Those two keys come together as a pair. They are related in some way. The idea is that one of those keys is secret, or a private key, and the other is a public key. That is, it's not secret. Anyone can know it. And we encrypt using one of the keys, and if the keys are chosen correctly, then we can decrypt only using the other key. So the benefit will be that if I have my own key pair, my own public and private key, I must keep my private key private, just to myself. I don't tell anyone. But my public key, I can tell everyone what my public key is. And then when you want to send something to me secretly, you'll encrypt with my public key, send me the ciphertext, and the algorithm will work such that only the person with the private key can decrypt. So only I can decrypt because only I have my private key. So we'll see this is the public key encryption, and it has the benefit in that it's very easy or much easier to distribute keys. No longer do I have to tell you a secret key in order for you to send something to me that is encrypted. Now I can tell everyone my public key, and anyone can send something to me encrypted, and only I can decrypt. So that is what we're going to cover in the next form of, or the next set of ciphers, public key encryption. But to do that and understand how those ciphers work, we need a little bit of revision and some new concepts on the mathematics that we need in number theory. So that's what this topic will be about. We'll introduce some concepts, some you'll know already. We'll give a few examples, and then we'll move on to the public key encryption tomorrow. Let's make some space for our examples. So number theory, so a discipline of mathematics that we're going to use to do public key encryption, and even some other things in the later topics. We're just going to introduce some very basics. Sometimes we will not derive the formulas or the theorems. We'll just say, here's the theorem, remember it, just so we can quickly go through this topic to set up for the next topic. First, let's look at basic concepts of divisibility and prime numbers, which I think you know about, just a refresher. We can say B, some number B divides some number A if A equals M times B, where M is some integer. Well, in fact, all A, B and M are integers. So we can talk about one number divides another, okay? If we're all integers, and the notation we can use is B vertical bar A. This is very basic mathematics, primary school mathematics, but we'll use this notation sometimes in later definitions and so on. So B is a divisor of A, for example. And then we have this concept of a greatest common divisor. Between two numbers, A and B, we shorthand GCD. The greatest common divisor of A and B is the number which can divide both of them, or it's as the name suggests, the number that can divide both of them, and it's the largest. And there are efficient algorithms for finding the greatest common divisor. So I think you know about GCD and division. A new concept, perhaps, to you is relatively prime. Two integers are relatively prime if their greatest common divisor is 1. And we'll use this concept in a number of our definitions. And sometimes I'll use a shorthand for relatively prime on the board, just RP. For relatively prime. All right, here's a question. Are these two numbers relatively prime? Why not? Okay, you've all picked up that they have divisors which are common, which are greater than 1. Okay, so the greatest common divisor is 12. 12 divides 24, 12 divides 60. So their greatest common divisor is not 1, therefore they are not relatively prime. As another example, what numbers are relatively prime with what numbers are relatively prime with 7? 1, 2, up to 6. Let's stop there. 7 and 1, the greatest common divisor is 1. 7 and 2, greatest common divisor is 1. 7 and 5, 1. So all numbers less than 7 are relatively prime with 7. Why is that? 7 is prime. So we'll see that defined, or we'll use that property shortly. If we have a prime number, all numbers less than it are relatively prime with it. So take the number 13. The numbers 1 up to 12 are relatively prime with 13. Okay, that's simple. What's next? Prime numbers. I think you know about prime numbers. Some integer p is a prime number if and only if its only divisors are 1 and itself. The only divisors of 7 are 1 and 7. Therefore, 7 is prime. Any integer, any greater than 1, can be factored into prime numbers. That's what this is saying here. There's any integer, whether it's prime or composite, can be factored into prime numbers. The notation is simply saying, well, sometimes it's written in shorthand, so some integer a, some prime number raised to some power, and of all sets of all value of prime numbers, there'll be some power here, whether it's 0 or greater. It's just saying that choose some integer, 1024, we can find, in theory, that it's fact that we can write it as multiplying prime numbers together. Take just prime numbers, multiply a selection together, and we get 1024. Any integer can be factored into primes. We'll use that later. This is just lists some of the prime numbers under 2000. That was easy. Now, modular arithmetic. we'll use modular arithmetic in a number of our operations in public key encryption. Let's define some concepts. So using the mod operator, which you all know how to use. If a is an integer and n is a positive integer, we define a mod n to be the remainder when a is divided by n. So there's finding the remainder here, where n is called the modulus. Two integers, a and b, are congruent modulo n if a mod n is the same as b mod n. And we will write that as a is equivalent to b mod n. Some examples. Or an example, 3 and 11 are equivalent. That's what we're saying in mod 8. Because 3 mod 8 is 3, 11 mod 8 is 3. So therefore 3 and 11 are congruent modulo in mod 8. That's the simple concept there. The mod n operator operates on all integers, and it maps them into some set of n integers, ranging from 0 up to n minus 1. The mod 8 operator can take as an input any integer, and the output of applying the mod 8 operator will be the integers the output will be the integers 0 to 7. So there's a fixed size of the output there. So it maps all possible integers into a fixed size set of integers, denoted as Z8 there. So modular arithmetic, which we're going to go through, performs arithmetic operations, addition, subtraction, multiplication, division, within the confines of that set, Zn. So arithmetic in mod 8 performs operations within this set from 0 to 7. Many of the rules of normal arithmetic that we know apply for modular arithmetic, involving addition, subtraction, multiplication, and so on. Well, those three at least. Some of the rules are listed here. Some of the laws that we know with normal arithmetic also apply for modular arithmetic. A mod, for example, A mod n plus B mod n, all mod n, is the same as simply summing A and B and then mod by n. And some other rules here. We'll just go through a selection of them. For example, we can expand a multiplication out. 11 times 15 mod 8, using this rule, can be expanded to be 11 mod 8 times 15 mod 8 all mod 8. And 11 mod 8 is 3. 15 mod 8 is 7. Which gives us 21 mod 8, which gives us 5. This can be useful in applying modular arithmetic on large numbers. Because you see, even in this simple example, I didn't have to calculate 11 times 15. What is 11 times 15? Okay, we don't know it off the top of our head. But I could find 11 mod 8 to be 3, 15 mod 8 to be 7, and I do know 3 times 7. So if we use large numbers, instead of 11 and 15, but very large numbers, then we can break that down into much simpler operations. And in terms of computers, that can speed up the computation time. So we can use these rules, not just for solving the simple problems in our head, but the computers will use those rules to simplify calculations when you use very large numbers. And very large numbers may be hundreds of bits in length. With 100 bits, for example, you have 2 to the power of 100 possible values. So much larger numbers that your calculator will handle, for example. What else do we need to know from here? A new concept, or something you may not have heard of, is the additive inverse. In modular arithmetic, addition is as you know it in normal arithmetic. You just add the two numbers and perform the modulo. With subtraction, we use the same concept as normal arithmetic, but it's slightly different from how we think or how we've grown up with it. We have the concept of an additive inverse. Maybe. All right, although it says division, in fact, let's go through subtraction first. Addition in modular arithmetic, you just add the two numbers and perform the mod. Subtraction, we have a concept of the additive inverse of a number. The additive inverse of some number is the number that we add to it that will give us the answer of 0, mod n. What's the additive inverse of 3 in mod 8? I've heard -3, I've heard 8. They're both wrong. Have I heard anything else? 5. Add the two numbers together and get 0. That's the same in our normal arithmetic. Someone said, in our normal arithmetic, if we have what's the additive inverse of 3, it's -3, because when we add 3 and -3 together, we get 0. But in modular arithmetic, we're operating in the confines of this set. In this case, Z8. We don't have negative values. So what's the value? The value that we add to 3 to get 0 in mod 8 is 5. Three and 5 are additive inverses of each other. All integers have an additive inverse in modular arithmetic. To perform subtraction, we will use the additive inverse. In the same way that we use the additive inverse in normal arithmetic. In normal arithmetic, to perform subtraction, we in fact do addition on the additive inverse. That is, 5 minus 3 is really 5 plus minus 3. That is, take 5, add the additive inverse of this value. The additive inverse of 3 is minus 3 in normal arithmetic. So subtraction is we add the additive inverse to the number. So now apply that. What's 4 minus 3? Why? No. Although you'll get the same answer. Let's see why. With subtraction, we add the additive inverse. AI means additive inverse here. 4 minus 3 is 4 plus the additive inverse of 3. 4 plus the additive inverse of 3 is, we know the additive inverse of 3 is 5. We got the same answer, but your approach was wrong. So be careful here. Okay, a few more just to make sure you understand or follow that. And the examples I'll do here are in Mod 8, just to keep things simple, but you can do it, it still applies in with any modulus. So I will not always write Mod 8 up here, but now we're doing it in Mod 8. What's the answer? In Mod 8, what's 2 minus 6? Two minus 6 is 4. And 2 minus 5? 2 minus 5 is 5. Two minus some value is 2 plus the additive inverse of that value. The additive inverse of 6 is 2, because 6 plus 2 mod 8 equals 0. From here, the additive inverse of some number is that number that when we add them together we get 0. So additive inverse of 6 is 2, 2 plus 2 is 4, mod 8 here. And you'll see 2 minus 5 is 2 plus 3. Everything's mod 8. So you need to go back to the basics of what is subtraction. It's adding the additive inverse. It's the same concept in our normal arithmetic. It's just in our normal arithmetic, we can do it directly. Or we've learned to do it directly. That's simple. What about multiplication? Multiplication is the same. Multiplication is just multiple additions. So in your head, multiplication in modular arithmetic is the same as multiplication in normal arithmetic. You just multiply the numbers, mod by the modulus. But what about division? Division, in the same concept as our normal arithmetic, we have a multiplicative inverse. That was an example of our normal arithmetic. What about division? What do we do? How do we think about division compared to multiplication in normal arithmetic? We multiply by the inverse. Four divided by 3 is the same as 4 multiplied by the inverse of 3, the multiplicative inverse of 3. The multiplicative inverse of 3 is the number that when we multiply them together, we get 1. The multiplicative inverse of 3 is 1 over 3, because when we multiply them together, we get 1. So that's our definition of multiplicative inverse. Two numbers multiplied together, answer is 1. Definition of additive inverse, two numbers added together, we get 0. So division, we simply multiply by the multiplicative inverse. Same applies with modular arithmetic. Two divided by 3. In mod 8 now. Now we move to mod 8. What's 2 divided by 3 in mod 8? Not 2. To do division, we'll need to multiply by the multiplicative inverse of 3. Where mi is short for multiplicative inverse. So that's division. 6 is the answer. So now the next step is, what is the multiplicative inverse of 3? It's the number that when we times it with 3, the answer is 1 in mod 8. Three times something equals 1 in mod 8, so that something is in fact 3, because 3 times 3 is 9, mod 8 is 1. Therefore, so just forgetting this part, from here, 2 times the multiplicative inverse of 3, which is 3, is 6. 2 divided by 3 is 6 in mod 8. So just be wary, in modular arithmetic, addition and multiplication are how you think about them. Subtraction, we instead add the additive inverse, where the additive inverse of some number is the number, when we add it together, we'll get 0. Division, we multiply by the multiplicative inverse, where the multiplicative inverse, two numbers multiplied together, we get 1 as the answer. What's 2 divided by 5 in mod 8? What's the multiplicative inverse of 5? 5. Because 5 times 5 is 25. 25 mod 8 is 1. Because 3 times 8 is 24. And the answer? 2. Everything's mod 8, remember. Maybe that was a bad example because we still get the multiplicative inverse is the same. One more example. Ignore that. What have we done? 2 divided by 3, 2 divided. Try 4. What's 2 divided by 4 in mod 8? No what?
No multiple inverse.
Okay. In mod 8, 4 does not have a multiplicative inverse. 4 times something we need that to be true. 4 times some integer, mod 8 will equal to 1. If that integer exists, then that's its multiplicative inverse of 4. But there's no such integer. So 4 does not have a multiplicative inverse in mod 8. So we cannot divide by 4. There's no solution. We cannot perform that operation. So all integers have an additive inverse in mod n. That's true. But not all integers have a multiplicative inverse in mod n. Some integer a has a multiplicative inverse in mod n if a is relatively prime to n. In mod 8, 3 had a multiplicative inverse. It was 3. 3 and 8 are relatively prime. The greatest common divisor of 3 and 8 is 1. 5 had a multiplicative inverse in mod 8. 5 and 8 are relatively prime because the greatest common divisor of 5 and 8 is 1. 4 does not have a multiplicative inverse in mod 8 because 4 and 8 are not relatively prime because they have the greatest common divisor of 4 and 8 have the greatest common divisor of 4. They're both divisible by 4. So no multiplicative inverse for 4. And you can check for the other numbers. Again, that's a principle that we'll see come into play when we look at the different ciphers. Multiplicative inverse and continuation onto exponentials. What's next? So the operations we've got in our modular arithmetic: addition, subtraction, where we need to know the additive inverse, multiplication, division, where we need to know the multiplicative inverse. What are two other operations that are common in our arithmetic? Addition, subtraction, multiplication, division. What else? To the power of. I can't say exponentiation, to use an exponent. That is a to the power of b. So what is that? Well, that's a combination of multiplication. Exponentiation is just multiplying multiple times. 2 to the power of 3 is 2 times 2 times 2. And what's the sixth one? Or the opposite operation to exponentiation? Logarithm. So two more operations. We'll come to them later with some different examples. But we'll see that exponentiation is possible in the same way that multiplication is. But the logarithm, in the same way that not all integers have a multiplicative inverse, we cannot do a logarithm in mod n on all possible values. And that is important in one of our ciphers later on. We'll give examples of that later. And that's a good place to stop. It's very basics. So we'll use those basics to go through some different theorems tomorrow, and then we'll use those theorems and those basics in some different ciphers tomorrow. So make sure you understand them, because I will not give more examples of them. You can try examples of those 4 operations, and we'll do them quickly in any examples for the ciphers. Let's continue tomorrow.